Okay, so now we're done with acoustics, wherein you have learned about the different properties of sound and the propagation of sound. Now we will move to our next topic, which is nature of light, or which is optics, wherein this time we are going to discuss about the nature of light and the different properties of light. And also we will have geometric optics, okay? So let's first have the nature of light. Okay, optics is considered to be a branch of physics which deals with the study of light and its different properties. So we will have the different properties of light under optics. Now, before we discuss the different properties of light, let us look at, before we discuss the different properties of light, let us look at the different scientists who have contributed in understanding of light. So we have first Christian Huygens, wherein he considered that light is a transverse wave. Now, can you recall what is a transverse wave compared to a longitudinal wave? Now, let's recall that sound is a longitudinal wave, wherein the propagation of sound, the direction of the propagation, is the same as or parallel to the direction of the particles. But if we will have transverse wave, that means that the direction of the particle's movement is perpendicular to the propagation of wave. So they are perpendicular, that is transverse wave. So Christian Huygens discovered that light is a transverse wave. We also have James Clerk Maxwell, wherein he has a discovery that light is an electromagnetic wave. And let's recall also that electromagnetism, so this is referring to a combination of electric field and magnetic field. So light is an electromagnetic wave. I'll show you an illustration later. Then we have Thomas Young, wherein Thomas Young, according to Thomas Young, light is a wave. This is supported by his Young's double-slit experiment. Now, there is a controversy wherein they are considering light as a wave, and also they are considering light as a particle. So how were they able to resolve that light is a wave or a particle? So Isaac Newton considered light as a particle by his corpuscular theory of light. So light is considered to be composed of corpuscles or particles. Okay? So they are also known to be photons. Now, the resolution for that, the combination of light being a wave and a particle, was answered by quantum electrodynamics. Now, this is also part of modern physics, wherein this one is a relativistic quantum field theory of electrodynamics. It describes how light interact, or how light and matter interact. This is also a theory wherein this time it includes both wave and particle properties of light. So light is a wave, or we have here the duality, the dual nature of light, light as a wave and light as a particle. The wave model would be very appropriate to describe the propagation of light, but the particle model will be the one, or which is very appropriate when it comes to discussing about emission and absorption of light, and that is under quantum electrodynamics. Now I want you to look at this one. This is an electromagnetic wave. Okay, the symbol for E here, that is your symbol for electric fields. The symbol for B, that is your symbol for magnetic field. Now we know that this is composed of charged particles. So charged particles are producing electric fields, and then also moving charged particles can produce magnetic field. Okay, so that's why you can see here a combination of electric field and magnetic field, and their direction, they are perpendicular to each other. So when we talk about waves, we are also going to talk about wavefronts. So when we say wavefront, we will consider the distance from the object or image point. It has equal radius of wavefront curvature. So itong mga curve na to, yan. So this is the wavefront. Okay? So if we are going to consider here, the distance, it has equal radius. Okay? So this is the wave, but this one would be the wavefront. This is another wavefront. Okay? Which is perpendicular to the propagation of the wave. So, ang propagation ng wave natin, the direction is this. Yan. So, this is another wave propagation. So, wavefront is perpendicular to the direction of the wave. Now, we have here different forms of wavefronts. We have planar wavefront for A. Then, we have spherical converging wavefront formed by a lens. So, you can see here that is spherical. And then, we have aberrated wavefront. So, they are in different directions. So, hindi smooth yung ating wavefront for letter C. Now, let's have the different properties of light. Take note that the speed of light in a vacuum is always equal to 3 times 10 to the 8 meters per second. Again, if this is in a vacuum. Now, I want you to look at this animation. This is a reflection of light. So, reflection of light is defined as the bouncing of light as it meets a barrier. Now, in your experiment, you have observed this one. You have here the blue line as the incident ray, and then the red one would be the reflected ray, and then we have the normal line, which is at the center, perpendicular to the barrier or to the surface. Then the angle from the normal line to the incident ray, that is your angle of incidence. And then the angle from the normal line to your reflected ray, that is your angle of reflection. Then according to the law of reflection, which you have discovered based on your experiment, the angle of incidence is always equal to the angle of reflection. When we talk about reflection of light, we have this specular reflection of light. So when it bounces through a smooth surface, so that is a specular reflection. But when you have diffuse reflection, that the surface is not smooth. If, for example, you are reading a book, okay, that is actually a form of diffuse reflection. Because of the print in the printed material, kaya nagkakaroon ng different directions of the reflected light. That's why you are also able to read that material because of the diffuse reflection of light. Now, sometimes also, total internal reflection happens. It happens when it meets the critical angle. So, you can see here, we have the light source. Okay, you can see here the light source. And then, this one is reflected, but some were refracted to the other medium. And then, on this ray also, this is reflected, and others are refracted. But, if it hits this surface at its critical angle, it will just be reflected. It could no longer go out of the medium. So that is total internal reflection of light. This happens if you have here a high index material. Light incident at any angle greater than critical angle is totally reflected. Okay, so that is total internal reflection. When do we use this total internal reflection? Okay, here are some applications of total internal reflection. We have the fiber optics, which is used in telecommunications. The signals are not affected by electrical storms. More signals can be carried with less energy source, and the cables also are smaller and lighter. So, yan, meron tayong mga pang-display din na it's like fiber optics, wherein you can see the light being transferred. So that is internal because of the total internal reflection of light. In medicine also, we have these endoscopes. One bundle carries light into the required area. So the light is just, we have a light source and then it will be totally reflected, while another bundle carries an image of the area back to a monitor. So yeah, it's also making use of total internal reflection. So those are just some of the applications of total internal reflection of light. So now let's talk about another property of light, which is refraction of light. So take note also that reflection of light, it actually portrays wave nature of light and also a particle nature of light. If we are going to imagine the particle nature of light in reflection, para siya yung bola, it hits the surface and then it will be reflected. So photons will move that way. So they will just bounce back, or they will just bounce following the law of reflection. The angle of incidence is equal to the angle of reflection. Okay, now let's talk about refraction of light. So this is a very simple experiment wherein you have a pen, then you have a glass of water, then you place the pen, and then it appears to be bent. Why is that so? Because light is refracted. So you can see here in the animation, or in this illustration, this is the wave propagation, and then you can see here the bending of light waves as it passes through different medium. Refraction of light, it is caused by the change in the average speed of light in going from one medium to another. For example, it comes from air, tapos nagpass through water or through glass, it will bend because of the different nature of the material. So the light will have or will change its speed as it passes through different media. We can also consider refraction of light to be a property of light being a particle. That a particle can actually change direction or can actually change speed as it moves to a different medium. Okay? So that is refraction of light. Now, an application of this is the formation of mirage. Okay, wherein, because we have different layers of air, we have hot air, cold air, and then light will travel at different speeds because of the different temperature. So it appears to be bent. Okay, there is a refraction of light and it appears to have reflection. So kaya parang may tubig dun sa area. So that is actually a result of refraction of light. We have here the index of refraction, N, is equal to the speed of light in a vacuum, C, and then we have the velocity of light at a particular material. So that's why you have here the N is equal to 1 in a vacuum, because C is the speed of a light in a vacuum compared to the speed of a light in a vacuum, so that will be equal to 1. So for this one naman, this is the speed of light in a vacuum, and then this becomes 1.0003 ang N, because we know that the velocity at air would be lower or slower than the velocity in the vacuum. Okay? So next, Snell's law. For refraction of light, we also have this Snell's law, wherein N1, or the index of refraction of the first material, sine theta 1 is equal to N2, or the index of refraction of the second material, sine theta 2. Okay, so let's explain this one in detail. So you have N1 sine theta 1 equals N2 sine theta 2. So let's recall that N is equivalent to C over V. So that means that when N gets higher, when N increases, so that means that the velocity here is lower. Okay, we have the velocity here is smaller compared to the C. So if N increases, velocity is lower compared to when N decreases. That means that the velocity there somehow approaches the speed of light or near the speed of light. So we have here V is faster. Okay, again, if you have higher N or higher index of refraction, that means it will have a slower speed. But if you have here lower index of refraction, that means that the velocity will be faster. So for example, the light travels from one medium to another medium wherein N2 is greater than N1. If N2 is greater than N1, so that means from ano siya, the light is coming from N1 to N2. But N2 here is greater than N1. So if N2 is greater than N1, so again, higher N, that means the speed will be slower. So if we have here the normal line, this is our normal line. Then let's say we have N1 here. This is the material N1 and the material N2. And then N2 is higher, or index of refraction for medium 2 is higher compared to N1. That means the speed will be slower. So if we have here the incident ray, and then this is the angle of incidence, this is always from the normal line. Since it will be moving at slower speed, so that means it will bend towards the normal line. So you have here smaller theta 2 is smaller than theta 1. Okay? If it will move slower, it will bend towards the normal line. Okay? So you have to take note of that. Again, if it moves from a material with smaller index of refraction to a material with higher index of refraction, that means it will be moving at slower rate, so it will bend towards the normal line. The angle will be smaller than the initial angle, or the angle of incidence. Okay, so take note of that. Let's have the other situation. Okay, let's say this time the second material is N2. This time N2 is lower than N1. So N2 is smaller than N1. So that means if it has a slower, or if it has a lower index of refraction, the velocity will become faster. So what will happen here? Okay, let's draw it again. Let's say we have here the incident light. This is the material N1. Here we have the angle of incidence, or the angle of incidence. And then what will happen to the refracted ray, or refracted angle? We now have here N2, wherein N2 is smaller than N1, but the velocity will become faster. So what will happen is that the light will bend away from the normal line. So looking at this angle, that's the angle of refraction, it has a higher angle compared to the angle of incidence. So if it's moving towards a material wherein it will become faster, it will move away from the normal line. But if it will move towards a medium wherein the velocity will become slower, the refracted ray will be bent towards the normal line. Okay? So you have to take note of those concepts. So just write your questions in the comments, or in the comment box in the YouTube, or in our group, okay, so that I can address your question when we meet through Google Meet. Next. Okay, one application of refraction. Do stars twinkle? Okay, stars actually do not twinkle, but they appear to be twinkling because stars emit its own light. However, before it reaches us, it will pass through different layers of the atmosphere with different densities. That's why they will be bending and bending. So twinkling of stars is actually a result of refraction of light. Okay? Okay, so now let's also analyze what happens to the light, or what happens to light as it refracts. Now we take note that the speed changes, but the frequency, or the number of waves passing through a certain point at a particular time, doesn't change because it cannot destroy waves. The barrier will not destroy the waves passing through it, so the frequency will remain the same. So looking back at our formula about on velocity or speed of light. Okay, so let us recall that velocity is equal to lambda f. Okay, take note again, frequency is constant. So it doesn't change even though there is refraction. So what changes would be the speed. Since the speed changes, therefore the wavelength should also change since this one is constant. Okay, again, if velocity changes, so we expect that there was a change in the wavelength of light because frequency was held constant. Okay, so let's identify that again. If frequency is constant, we can derive the equation for frequency. We have here frequency equals velocity over lambda. Okay. If, for example, light is in a vacuum, we now have frequency is the speed of light divided by lambda in a vacuum. So you have here again, frequency is constant, so you have velocity over lambda. And then if we refer to light in a vacuum, we now have c, which is the speed of light in a vacuum, divided by the wavelength of light in a vacuum. So we now have another equation wherein velocity over lambda equals c over lambda naught. So if we want to get the wavelength of the light, we now have here wavelength is equal to, we cross multiply, so we have c wavelength equals v lambda naught. But we have here for lambda, we have v lambda naught divided by c. But let us recall also that n is equal to c over v. So you have here the reciprocal of n. So we now have a new equation wherein lambda at a second material, for example, from a vacuum to a second material, the lambda will become lambda naught, which is the wavelength of light in a vacuum, divided by n. Okay? So this is our formula for the wavelength. Okay, so that is another equation that you have to remember in optics. Lambda is equal to lambda naught, wherein lambda naught again is the wavelength of light in a vacuum divided by the index of refraction of the material. Okay, so next. The next property of light that we are going to discuss would be the diffraction of light. Now, you have encountered this property already when we discussed about sound, wherein wave is diffracted as it passes through a slit. So, diffraction of light is defined as the bending of light as it passes through a slit. The smaller the opening or the slit, the more the light will become diffracted, or the more the light will be bent. Another property of light is interference of light. When you have waves, say we have here two slits, and then we have two waves here, then they interfere or they meet one another. When two waves meet in a medium, they combine. So it will result to constructive interference. If, for example, crest meets crest and trough meets trough, so we have constructive interference, it will produce light. So yan yung mga may light bands. That is a result of constructive interference. But if you have, let's say, crest meets trough, you will have destructive interference and it will result to dark bands. Okay? So that is about interference of light. Now, another property of light, take note also that diffraction of light supports the wave nature of light. The same with interference. It also supports the wave nature of light. But you have here polarization of light. This one also supports the wave nature of light and doesn't support the particle nature of light. Because imagine, if we consider light to be particles, then all the photons will just pass through this one. Kahit ano pa yung orientation ng ating polarizer, it will just pass through it. But for the concept of polarization of light, for example, you have here three waves. We have the green, the orange, and the blue one. But we have here the orientation of the polarizer. or the polarization filter with vertical passage, it will only let the vertical waves to pass through it. And then nafi-filter niya yung iba. It will no longer pass through that filter. So that is polarization of light. Now, one application of polarization of light is this. Polarized light waves are light waves in which vibrations occur in single plane. So we have here yung 3D movies. It works because of polarization of light. So when you watch, you have here two different polarizer or polarization filters. One is oriented vertically, then the other one is oriented horizontally, and then it will polarize the light waves. Now, since they have different orientations, yan, it's actually creating depth. So it appears to be 3 dimensions. So that's about the different natures or the different properties of light. Now let's look into the problem solving on the different properties of light. Okay, so now let's solve this problem. What is the speed of light in water? Okay, recall that we have here n is equal to c over v. And then the n for water is equal to 1.33. So here we can solve for the velocity. Let's derive an equation for velocity in water. So you have velocity is just equal to c over n. So our c is 3 times 10 to the 8 meters per second divided by 1.33. So we'll have an answer equal to we will have an answer equal to 2.26 times 10 to the 8 liters per second. So that is the velocity of light in water. Okay, let's now have the next problem. An incident ray of light from air strikes a flat glass at an incident angle of 35 degrees. What is the angle of refraction if the glass, or in the glass, if the index of refraction in glass is 1.5 and the index of refraction in air is 1.0003? Okay, recall that Snell's law tells us, or recall that the equation for Snell's law, we have here n1 sine theta 1 is equivalent to n2 sine theta 2. So you're given here, we have the incident ray of light is coming from the air, so n1 is air, and then you have here n2 is for the glass. We are looking for the angle of refraction in the glass, therefore we are looking for sine theta, or angle 2. So you have here sine theta 2 is equivalent to n1 sine theta 1 divided by n2. So for us to be able to get the angle theta 2, you just have to get inverse sine, or sine negative 1, then the quantity n1 sine theta 1 over n2. So let us now substitute the given. We have inverse sine. Again, our n1 is air, so you have 1.0003 or 1.0003. Then you have the angle for the incident angle is 35 degrees, so you have sine 35 divided by, we have n2 which is the index of refraction in glass, is 1.5. Okay? So let us solve so that we can get angle theta 2. So our theta 2 is equivalent to, okay, so we have here our answer is 22.49 degrees. And 22.49 degrees. Okay, let's take a look at this. The incident angle is equivalent to 35 degrees. And then here, the refracted angle is 22.49 degrees. Therefore, it moves, or it bends towards the normal line. So the angle decreases. That means that the light slows down in glass compared to the velocity of light in air. So that's how we analyze the answers. Okay, so let's now have the next item wherein you have here the air. The incident angle is 30 degrees, and then it goes to the glass wherein we are looking for the refracted angle. So theta 1 is 30 degrees, and for air it's 1.0003. Then and for glass, we have used 1.5, so we will just use 1.5 also. Kindly round off the 1.46 to 1.50. So let's solve for theta 2. Okay, so we now have n1 sine theta 1 equals n2 sine theta 2. So again, we are looking for theta 2. So you have sine theta 2 is equivalent to n1 sine theta 1 divided by n2. Or for us to be able to get theta 2, that should be inverse sine. Then the quantity n1 sine theta 1 divided by n2. So here you will be able to get angle 2. So we have angle 2. Let's continue. Here again, our formula is theta 2 is equivalent to inverse sine n1 sine theta 1 divided by n2. So we have our n1 for air. Our n1 is 1.0003. Then sine 30 degrees divided by our n2 is 1.5. Okay, let's take a look at the answer. Okay, so let's now have our answer. This is equivalent to 19.48 degrees. So take note again that the angle decreases, so it bends towards the normal line. So that means the velocity becomes slower. So let's solve for the velocity. We have here velocity 2. Again, n is equal to c over v. So let's solve for the velocity in glass. Okay, so we have v is equivalent to c over n. So our c is 3 times 10 to the 8 meters per second. Okay, divided by the n for the glass is 1.5. So the velocity in glass is equivalent to 3 times 10 to the 8 divided by 1.5, which is equal to, okay, this one is equivalent to, okay, solving this one, this is equivalent to 2.0 times 10 to the 8 meters per second. So that is the velocity of light in the glass. Okay, so we have here the velocity in glass, but we want to look for the change in speed. So let's also solve for the velocity in air, wherein n is equivalent to 1.0003. Okay, so we have again n is equal to c over v. So if we wanted to look for the velocity in air, we have v is equivalent to c over n. So we have here velocity in air is 3 times 10 to the 8 meters per second divided by n is 1.0003. So we have the velocity in air is equivalent to 3 exponent 8 divided by 1.0003. The answer is 2.99. 1 times 10 to times 10 to the 8. So almost 3. So we'll just write 2.99 times 10 to the 8 meters per second. But the velocity in glass, we have 2 times 10 to the 8 meters per second. So there is a difference of 0.99 times 10 to the 8 meters per second, or the delta V. Since the final velocity is lower compared to the initial velocity, we now have negative. We can express it as negative 9.9 times 10 to the 7th meters per second. So that will be the difference in the velocity or in the speed when we compare the velocity in air and the velocity of light in glass. Okay? So that will be the end of our problem solving in this part, or in this properties of light. So we'll just have the seat work by next meeting. Bye everyone!